Hello again, folks. I'm sorry, I always seem to be creeping in here. It's good to see you, hopefully soon. Today we're going to cover section 5, 6, and then at the end I'll just give you some reminders, as usual. Basically today, if you've been following along in the calendar, we should have had test number 2. As I told you last time, we can't have that obviously because we can't meet. So I took the time to do 5, 6 today, and then we'll be back on schedule, which means that on April 1st, April Fool's Day, right, we'll be doing 5, 4, right, which is right where we're supposed to be. Okay. And I'll put this aside. All right. Let me give you an overview of what is covered in section 5, 6. I hope I didn't say 5, 3. I feel like I did somehow, but 5, 6. Okay. In 5, 6, there's 3 things basically. There's the rules of exponents, which is a handout that I would give you. There's conversions, and the end of it will be just a review of how to use a calculator. Let's see, it's a Texas Instrument calculator technically. All right. Of the rules of exponents, you'll see them. There's 5 that your textbook has specified. I'm going to give you 7 just because I had prepared this slide, this handout a while ago, and I think it's practical information anyhow. This is a handout, which I'll show you in a moment. There's several of these. Of conversions, let me just get this terminology out of the way. There's the regular ordinary way that a number is written, which in some textbooks is referred to as standard form. The standard way to write. In your book, I want to say that they're calling it decimal form. Right? And what you could do with that is you can convert it to scientific notation, which is more or less an abbreviation for either very large or very small quantities. Right? And you could convert backward if you need to. Right? This is practical if you go into a science, right, or if you go into engineering, because you deal with astronomically large quantities, or you deal with very small things, microscopic, nanoscopic, or whatever. Anyhow, for right now, just convince yourself, standard form, decimal form, that's the regular way that you see a number. All right, and scientific notation, by contrast, looks like this. There's some number and sitting in front of a decimal point, it has to be a non-zero, so 1 through 9 Arabic numerals. Maybe something after it, that's up for debate. Could be several somethings. And then a power of 10. All right, and the power of 10 is what controls basically the number of decimal places that it's abbreviating for. Anyhow, if you see anything with one number sitting up in front of a decimal point and then times 10 to some exponent after it, most likely it's scientific notation. There are some technicalities, like I said, it has to be a non-zero up in the front. And if it doesn't include that, if you have maybe 2 or more digits up in front, it's not technically scientific notation, even though it suspiciously looks like it. Okay? Let's see. All right, now let me show you the handout that I would have given you. And I have it posted in Canvas as always. This is basically a summary of 7 rules for exponents. All right. these things up in the thought cloud here, I kind of added as an afterthought. They're kind of special, and we'll discuss them. But try to print this if you can help it. Right? I know that we're all working under, what's the word? Arduous conditions right now. But try to print this or duplicate it. Right? You could freeze the video if necessary and draw a diagram. All right, let me erase this. And then we'll go through several of these. Okay. Let's see. First of all, let's talk about the exponents in general. There's really two ways that you deal with them. How to deal with exponents, depending upon which branch of mathematics you're discussing. There's the plain old arithmetic way of dealing with them. And then there's more the algebra. And the difference really being that in algebra you deal with letters, of course, variables. So you're more inclined to leave things in the style of the abbreviation. Whereas in arithmetic you have actual numbers to work with, so if you can do the multiplication, you really do. Right? You still use abbreviations in either case. You use exponents for abbreviation. In both instances. But in the case of arithmetic, not always, but often, right, you do the actual multiplication involved. Give you some examples to illustrate. For example, if you had something like 2 to the 4th, 2 squared times 2 to the 4th, right? The very first rule that gets discussed, and I'll point to it here, is the product rule. And the product rule essentially says that if you are multiplying the same bases, in the diagram I have here I use letters, x and x, but if they are the same, regardless of what letter or number they are, as long as they're being multiplied, and you see this dot here, what you could do to sort of abbreviate this is just simply add the exponents. So whether you have letters or numbers to start with, in this case it's just arithmetic, you could do that right now. The product rule says that you could add these, in which case you would write it as 2 to the 6th, which is 2 plus 4. All right. Now, because it's relatively small, all right, and it's kind of arbitrary at this point, when to multiply, when not to, I would say if the base number is a single-digit number, and this is also a single-digit number, the exponent, and it's not too high, like not greater than, say, 5 or 6, right? Do the actual multiplication unless it's specified in your instructions. But here's what I mean. Let's expand this. If you were to write 6 iterations of 2, that is 6 little clones, if you will, of 2, 2, 2, 2, 2, 2, 2, and multiply them, you will get an actual regular ordinary number, right? It's a little tedious, especially without a calculator, up to a certain point. Like even 6 is debatable, but it's not impossible for a person to do it. This is an expansion, a product expansion, and it is literally what this would translate to, right? Here's the abbreviation, which is perfectly fine. Here's what the expansion would be, and then you could do the multiplication to get the actual number. So I'll do that really quick. This see if this writes as green. Okay. 2 and 2 is 4. 4 and 2 is 8. 8 and 2 is 16. 16 and 2 is 32. 32 and 2 is 64. So it means what this represents is the number 64. Okay. If, on the other hand, you had letters, and I'll sort of scribble a little separator here. This mark is on its way out. I'm going to have to replace that. All right. So there. If, on the other hand, you were using a variable, let's just say you had n, and I'll use n to the 4th times n to the 9th. All right. Again, according to the product rule, the product rule basically says that when the bases are the same, and they're being multiplied, you add the exponents. So, these bases are n in this case using a variable. It's more algebra than it is arithmetic. And they're being multiplied, hence the dot. So you add these exponents to abbreviate. And you have n to the 13th. Which I admit, not the most satisfying outcome in the world, but it is arguably more concise to express the quantity that this product would represent as this abbreviation. 13 iterations, I-T-E-R-A-T-I-O-N-S, iterations of this, meaning you wrote the number n, or pardon me, yeah, there's a number technically, but you wrote the letter n 13 times. 13 clones, if you will, of this base number. I prefer to say clones myself. Okay. Here's a practical usage of this, especially from the perspective of arithmetic. If you had to simplify, there is an advantage to writing out the expansion. Product expansion. If you had, say, 2 to the 5th sitting on top of 2 to the 3rd, right? You could figure out what this number is. It would be 32, technically, and figure out what this number is. That is translated. That looks too much like an exponent. This would be 8, because it's 2 times 2 times 2. And then divide these and get the answer of 4. Right? There's no sin in that. Right? Especially if you happen to have a calculator handy. Right? Here's the calculator, the TI 30X2S that we were requiring for this class, right? Or at least a scientific calculator. You could easily type that in there and it spits out the answer. But you don't need to go to your calculator for everything. You could, with a little bit of strategy, and some confidence, right, expand these two and then cross out some similar factors. For example, if you see 2 to the 5th, that's how many 2's? 5 2's, right? And in theory, it would be sitting above 3 2's. And they're all being multiplied, because exponents is a amped up version of multiplication, really, a very specific version of multiplication. It's a slightly more complicated one. You could pull that trick from when we were discussing greatest common factor. The greatest common factor would be, in this instance, circling pairs of 2's, all right? And you would have 3 pairs of 2's, and then you would prove that 8 would be the greatest common factor. In this instance, use this for the sake of cancellation to get to the quotient in this case. If this is in factored form, and it indeed is, what you could do is cross out pairs of like factors. So, right, they're gone, and then the leftover, and it's on top, would be 2 times 2, which is the same quantity 4. Anyhow, that's may seem like it's more trouble than it's worth, but it is kind of satisfying if you rig something, especially something more complicated than these, and you do not have a calculator. Just take advantage of that. If something is in factored form, you can always cross out pairs of like factors, whether they're a regular number or they're like an algebraic expression, x plus 2, you know, sitting in its own little parentheses on top, and the same thing, x plus 2 on the bottom. Okay. Anyhow, that is essentially the product rule. When the bases are the same and being multiplied, you add the exponents. Let's go to the polar opposite rule, which is the quotient rule. And the quotient rule could have actually solved our last problem exactly the same way. Let's see. The quotient rule, I-E-N-T, quotient, right, is a situation in which when dividing like bases, or the same bases, same difference, you instead subtract the exponents. This is on my diagram, the far end of the paper. I'll point to it here. This is this situation. When you have the quotient rule, if you have matching bases and you know that they're being divided, then you basically subtract the exponents, which I put in red. Okay, so let's look at the last problem. The last problem was 2 to the 5th over 2 to the 3rd. Right? You already know what the answer is, because we did it 2 different ways. Right? We did it more or less brute force dividing, and then the expansion to cross out pairs of factors. But if you employ the quotient rule, you, in recognizing that these are being divided and they're the same bases, if you were to subtract these, just realize that this is the same outcome. Be careful. Whatever is on top should be on the left side of the subtraction, right, sign. And whatever is on the bottom, that should be on the right side. Right? So if you had the problem flipped upside down, 2 to the 3rd on top, you'd have the 3 in front. And it's important because you would get a different answer. There's no commutative property of subtraction. Anyhow, 5 minus 3 is still 2, so that means it's 2 squared. And if you actually did the multiplication, you'd get 4 again. Here's a different problem. If you had 3 to the 7th over 3 to the 5th, and you use again the quotient rule, subtract these. That's my dud, I gotta get rid of that one. Okay, put that there. 7 minus 5 is really 3 squared, which is 9. Okay. As is often the case in math, there's more than one way to do something. And in the end, I would just simply advise you, just be aware of your choices. Right? And do what you feel most comfortable doing. Eventually, after a while, you build up enough confidence and you're okay doing it in one circumstance or another. And you might be more strategic. You'll do one problem one way and a different problem another way. That is legal. Okay. Now there's this. In my diagram, I put this up in a thought cloud. But let's do this in order here. The 0th power rule. Oh, squeaking. I wish my green were not so faint. I just bought green too. I don't know why it goes so quickly. This you could kind of think of as being where arithmetic meets algebra. And remember, arithmetic is the foundational technique. I'll put a little heart here. Right? I love you, math. Here's to illustrate something that you probably take for granted. Right? If you were to say this out loud to yourself, right? You know, what is a number divided by itself? Right? You might sit there and ponder it for a moment, right? And you'd say, well, although it depends, it's probably equal to 1. And for the most part, that is true. There is one exception. The exception being you can't divide by 0. Right. And here's some proof of that. If you had 7 divided by 7, a number divided by itself, I'm just writing it more or less stacked in the fraction-esque sort of way. A number divided by itself is 1, right? Even if it's something rather large. 105 divided by 105 is a number divided by itself, so it's 1. What about something mysterious? How about x divided by x? Granted, I don't know what x is, right? But by sheer logic, at least if this logic follows, assuming that x isn't also 0, which would be dividing by 0, right? And that is a mathematical impossibility, you would get 1. This is more or less the arithmetic perspective of things, right? And what we'll do now is apply the quotient rule. Let us say that we had a slightly more complicated version of this question. Something divided by itself, that is the same bases, and they have identical bases and also identical exponents. According to the quotient rule, I should subtract these. And that's fine. If I subtract these, then it would be x3 minus 3. And 3 minus 3 naturally would be 0. Okay. That is the abbreviation using the quotient rule. This is the outcome using arithmetic. That's why I say the 0th power rule is basically where algebra meets arithmetic. Right? On the paper, diagram and handout, here's how it is illustrated. A as in almost any base to the 0 is equal to 1. Right? The exception being the base can't be 0 itself. That would imply that you would be dividing by 0, right? You can divide into 0, you can't divide by it, right? It defies logic. Anyhow, think of it as such. A as in almost anything to the 0 is equal to 1. So if you see a negative number here, all right, that is if it's grouped like that, to the 0, it's 1, right? If you see a positive number here, to the 0, it's 1. Okay. Here's some examples to look out for. Do be mindful, pay attention to how things are grouped, because that would affect the answer, right? How things are grouped. If something is inside parentheses or outside parentheses, means that it's being grouped or not grouped. Grouped or excluded, if you will. Shunned. Mathematically shunned. Which is terrible. Okay, here's some examples. All right. If you had 2 to the 0, that's almost any base, right? Not 0 itself. One could say that this is going to be 1, right? What it really represents is, say, 2 to the first over 2 to the first, which would be 2, 1 minus 1, which is 2 to the 0, right? Something divided by itself is 1. If you had this even, negative 2 to the 0, this would also be 1, right? For this reason. Let's just say that it's negative 2 to the first over negative 2 to the first. Something divided by itself, a negative divided by negative is positive. This is a positive 1, technically. So you would have this situation, 1 minus 1, which would be 0. Almost anything, with the exception of 0 as a base itself, 2, 0 would be equal to 1. Same situation here. Do be careful, again, of these two situations. This especially, if the sign is grouped outside, you see, I put this as a little bullet point, if you will. If you see a negative, that's distracting, I'm gonna get rid of that. Doesn't look good on film, right? If you see a situation where the negative is grouped outside the parentheses, that means that this is the only thing that is being influenced by the exponent here. So although this might be 1 itself, you have to sort of remember to attach the negative as an afterthought. And this is also true if you have letters attached somehow. I don't think your book has too many of these, but if you had some variable, an algebraic expression like this, right? If the 0 were applied to both the x and to the 2, both of them would be this situation. The 2 would be that, the x would be that. Right? There's a rule which your book doesn't go into, all right, that I'll mention now. Right? This is an example essentially of the third one here, the product to power rule. And that essentially is when you have two distinct bases inside of a parentheses. I did put a dot here, and there isn't a dot in the example, but one could assume that these two things pressed together are being multiplied just the same. It's kind of like distributed property. Distributed property would be more appropriate to label something when there is a coefficient of normal size font sitting up in front of the parentheses where my finger is. But you know that when you distribute something, you give it, let's just say 1, to each of the contents via multiplication. kind of treat an exponent like that. You give it, or you apply it to each of the contents in the parentheses. That's why you would end up with a situation like this, right? A, in this case x, right, to the 0 would still be the amount of 1. 2, as we have done several times, is already 1. 1 times 1 is 1. Whether you have a letter or not. Right? Anyhow, officially that would be called the product to power rule. Kind of treat it like distributive property. It isn't technically because it's not a coefficient, it's an exponent, but has the same effect. Give the outside to each of the contents of the inside. Then there's another interesting case. 0, the negative exponents rule. Yeah, I'll use blue in some kind of cheesy attempt to make it cold, right? I don't know why I felt like that should be the color. Blue is in cold, right? Negative. Silly man. Negative exponents rule. And blue is starting to fade out here. Okay. There's another one. It's a little bit more fresh. Wish I could draw a straight line to save my life. Essentially, the negative exponents rule is like an abbreviation for a fraction. Here's what I mean. I believe on the diagram that I have given you, there's this model. A to the n, and when the exponent is a negative. How you would translate this? Basically, you would take whatever quantity you see and make it a denominator. So this A would move down essentially below a line here. And you'd have the same exponent. But once you do that, and it would be optional to write this, this becomes a positive in this location, just making this adjustment. Think of it as basically making an adjustment. Well, the dolphins are back. Click, click. Interspecies communication. It's the future. Would be a good thing, right? They can tell us a lot of things. I don't want to go off on that tangent. I'm slowly slipping into madness here in my hallway. Don't let this happen to you. All right. If I were to complete this thought, and I definitely should, I can't just leave a fraction without a numerator. So assume that you will put the number 1 there. Okay? Again, not to beat a dead horse here, but this is in this little thought blurb over here, summarized. Okay. Here's a couple of examples to illustrate. If you had 3 to the negative 2, right? Make the adjustment first. Don't attempt to do, like 3 times 2 is negative 6 or something like that. First of all, that is incorrect because it's supposed to be 3 times 3. And don't worry about the multiplication rules of signs when you're dealing with the exponent here. the multiplication rules for signs do not apply to the exponents. All right. When you're just applying the negative exponent rule, don't worry about that. It's not like it's this times this. You would end up with this to start with. Moving it from essentially top tier to bottom tier changes it to a positive. Why? Because this is really an abbreviation for a fraction to begin with. And then you could do the multiplication. 3 squared is really 9, so this is representative of 1/9. If, on the other hand, you had, this is a problem, where the thing starts as a denominator, 2 to the -5th, you could move this to just the opposite, right, tier. It starts out as the bottom, the denominator, if you will, and then if you move it, for the sake of dismissing this negative, right, it's considered, shall we say, bad etiquette to keep a negative exponent. If we, to conform ourselves to good manners, if you will, move this and it becomes 2 to the 5th on the top tier. Right? It is essentially, if you don't want to say the word fraction, it is making reciprocals, which is a fraction flipped upside down, right? Whether it started on top or it started on the bottom, right? It's going to the opposite location to adjust it. Right? Anyhow, at that point, the 1 is superfluous. You don't really need it. And this would be 32. Okay. I don't want you to think that this particular 1 here is the one that moved here. It really didn't do that, right? I put this 1 here unnecessarily, right? Only because it was a fraction to begin with. I wanted you to see that it is above the line, right? If this number that is sitting up on the top were, let's just say x, right, then it would still be there after the fact, right? If it was some other number, if you had 7 sitting up here, then it would still be here after the fact, because it is not being influenced by this negative exponent at all, right? Don't just shift the top automatically, just shift the location of the thing that has the negative exponent. Shift location of the base with exponent, negative exponent only. Okay. One more and then we'll discuss scientific notation. The power rule. When I made my diagram, I had designed it to discuss the power rule immediately after the product rule because I think people confuse those most often. They look similar. Here is the power rule. For exponents, of course. The power rule is you have a situation in which it is an exponent raised to an exponent. For abbreviations. And in which case, what you do is you multiply these. Alright, I'm going to draw the the power rule immediately next to the product rule because I don't want you to confuse them. Here is the power rule as an example. Here is the product rule. If you had x squared times x to the third versus, let's see, x squared being cubed, right? The power rule, you would see parentheses first of all, right? In this product rule, you don't really need that. The product rule tells you if the bases are the same, that you add the exponents. Whereas in the power rule, if you have an exponent raised to an exponent, you multiply the exponents rather than add them. Sorry if that's a little faint. The queens never write so great. Anyhow, these are the same bases being multiplied themselves. This is where the confusion comes from because it's a multiplication problem. But you add these, in which case you get what? X to the fifth. When you have an exponent raised to an exponent, the 2 being raised to the 3, you multiply these, in which case you get x to the 6th. The only instance potentially where you would get the same answer, whether you did it one way correctly or incorrectly, would be if it was squared, you know, because 2 times 2 just coincidentally happens to be 2 plus 2. There isn't any other instance where that is true. Off the top of my head anyhow. Anyhow, conform yourself, all right, distinguish these 2 rules. All right, the power rule is an exponent raised to an exponent and you actually multiply the exponents. The product rule, ironically, is when you have the same bases being multiplied, but you add the exponents. Okay, here again is my diagram. I put them next to each other on my diagram on purpose. Product rule, power rule. All right, let's get into scientific notation. As mentioned before, scientific notation is a convenience. It's an abbreviation, if you will, because it involves exponents for either very large quantities or very small quantities. So think of that. Scientific notation. Think of it as being an abbreviation very large, exaggerate this, large, or very small, small, quantities. Okay, and by large, I mean astronomical sizes, right? Something as big as a planet. Something very small is something being microscopic, you know, or even smaller than that. You can translate any number, any quantity, into scientific notation. Let's call it Psi-naught. It is possible. It just isn't necessarily practical. It's practical when the thing is very large or very small, because it spares you some trouble. To illustrate that point, right? I would have given you this, but if you could, try to print out this diagram, because there's two interesting examples here that will show you how to translate. And I'll discuss it now. This is again in Canvas, in the page that says materials for chapter test number 2. Okay. Let me erase this. This is essentially its purpose. Now let's do some examples. Trying to see if that's in frame. I'm sorry. Just want to make sure that this is not moving around too much. I'm leaning at an angle here, so it's a little weird. Okay. Okay. Forgive me while I write this because it's meant to really give you a feel for it. Right. If you had a number like this, 1, comma, and I'm conforming, mind you, to the style of writing a number in the way that it was taught in the United States. So we use commas basically on the left side of the decimal in groups of 3. 989, comma. And then behold, 9 groups of zeros in sets of 3. I may not even be able to fit this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Really squeezing it in there. And the decimal would be here. That's horrible, isn't it? First of all, you're not responsible for the place values that would be naming this number. Right? Have you noticed that in these science classes that, especially if you're in chemistry or in a laboratory class, that when you call out a decimal between two people, you measure something with your calipers or your instruments of some sort, that you refer to, 9.2 or whatever. You don't use the English equivalent of, whatever the suffix would be, tenths place, like, oh, it's you'd say 0.3. You wouldn't say 3/10, of a gram or what have you. That's fancy, basically, if you use suffixes like that. And in grammar school and elementary school, here, we teach kids to talk that way. Why? Because it's helpful if you're trying to convert from a decimal to a fraction, because it implies what the denominator would be. Tenths is implying that a denominator is 10. However, on the flip side, you can see how impractical it is to name something like this. I'll show you, and I'll attempt to answer to say it in English, but look how cumbersome it is. As ones, tens, hundreds, the first 3, right? To the left of the decimal. Thousands, 10,000s, 100,000s. These would be the millions. And then in the United States, we have the second set as the billions, and the third set as the trillions. There is some discrepancy outside the United States. I want to say trillions is 1,000 billions, or that's what we have. Or it's switched somehow, I forget. Trillions. I like my own cultural way of saying it, for the reason that, well, it's kind of like things that have wheels. A bicycle has 2 wheels. This is the second set of 3s after the first. A tricycle has 3 wheels, So then it helps me figure it out. This would be quadrillion. And this would be, I believe, quintillion. This is sextillion. Septillion, or septa perhaps, septillion? I think it might be septa as opposed to sept. I'll have to look into that. Tillions, octillions, and nontillion. Nana, maybe nana. Tillion. Anyhow, you can see that even figuring out the nomenclature, the system for naming this, is quite cumbersome. We're basically expected to know up to probably something like the millions place, because how often does anyone deal with that much money, right? If only we did. All right. This is one either nana, and one that looks like 1 nontillion, 989 octillion, and then whatever the unit would be. All right. If this were the mass of the sun, and I believe it is, in kilograms, that's quite large. And you thought that you were off your diet. Right? Jeez. Bad dad jokes. Okay. Yes, 1 nontillion, 989 octillion is a vast quantity that should be the mass of the sun. Anyhow, it is rather cumbersome to physically even write this across the board. Imagine doing it on a piece of paper. So let's change this. Let's translate this into the abbreviation that is scientific notation. For something to be in scientific notation, it must basically fit into a model like so. There would be a digit sitting up in the front, and then whatever amount of digits after it, barring some situation where you have significant figures. You don't have to worry about that. Times some 10 to some exponent. Anyhow, if you can imagine taking this decimal point, which would be after the ones place on the very, very far right, and moving it to just in between the 1 and the 9, right? You can translate this vast quantity into the abbreviation. And it would be 1.989 times 10 to the number of spaces moved. So I would have to count by threes, right? This would be 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. I would have to move the decimal point 30 spaces to write this abbreviation for the mass of the sun in kilograms. 1.989 times 10 to the 30th kilograms. All right. Even though that might be a little alien if you've never seen scientific notation before, and this is officially scientific notation, it is arguably more concise and more practical because I'm even just saying it as 1.989 rather than 1 and 989 thousandths, the English grammatical equivalent. All right. So you see that is practical. Okay. Anyhow, if you're a little worried, perhaps you've done this before, about the sign of this, all right? I don't want to really get you to memorize a sign, positive or negative, for the exponent until we get to converting from a regular standard number back, converting from scientific notation into a regular number, all right? Because the rules will be conflicting. So I'm kind of reserving the conversation of positive one direction, negative another direction of movement for that, right? For right now, what you really just need to convince yourself is this. And this works just as well. Associate in your mind very large quantities with a positive power of 10. very small quantities with a negative power of 10. Large, like astronomical sizes, anything technically greater than 1. Large is ironic, right? It's kind of arbitrary, right? Greater than 1, all right? Small as in tenths place, you know, like a decimal, you know, less than 1. As having a negative exponent versus a positive. Large positive power of 10, small negative power of 10. Let's do a negative. An abbreviation for something very, very tiny, which ironically will have just as wide a number, or almost as wide. Here is, for example, the mass of an electron. This is also almost as challenging. Let's see. Yeah. 0. And again, I'm conforming to the syntax basically of the United States way of writing a decimal. We don't use commas on the right side to group things in sets of 3. We're supposed to, I've seen textbooks not do this, but we're supposed to group things in sets of 3 and then leave an obvious space in between to make it a little bit easier to read. We don't use commas. So here's our first set. I'm going to leave a gap, which unfortunately might get me in trouble because I might run out of space. I'll be more concise. Kilograms. Okay. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups of 3. All right. Imagine finding out the suffix, you know, the appropriate pronunciation for the place value that all the way over there. All right. I don't know it offhand, but we could infer, right, if we had to. You will not be responsible to do that, right? To know that this is the tenths, the hundreds, the thousands, the 10,000ths, the 100,000ths, and the millions. That's pretty much where the state of New Jersey, in its infinite wisdom, has decided that we know up to, all right? Anyhow, if we were going to, again, conform to this model for scientific notation, which again is to have one decimal non-zero, has to be a non-zero, up in the front, the decimal point, and then whatever trails it, times the power of 10, it would be a matter of moving this decimal place all the way to in between the 9 and the 1 here. So I'm going to jump 3, 6, 9, 12, 15, 18, 21, 24, 27, 30 would be just in between 0 and 1. And then I would have to go a smidgen over one extra space to put the 9 up in the front. And we should do that. There are times when, unfortunately, you see something that looks suspiciously like scientific notation, but it isn't technically, because it has to have a non-zero, one digit up in the front. All right. So 9.11 times 10 to the number of spaces I would have moved would be 30, and the extra 1 would be a power of 10, that is the 31st. All right. Now remember what I said before. Don't worry about a direction of movement yet for subscribing a negative or a positive to this. just reason it through like so. Is this a very small thing or a very large thing? The mass of an electron. I would argue that it is a very tiny thing. So the abbreviation would need to be a negative, right? This power of 10 is some number like, you know, if it was much smaller, 10, 100, 1,000. And the effect of multiplying by 10, 100, or 1,000, or 10,000, or what have you, is that it simply moves a decimal point, right? So rather than dwell upon that, that's the minutia, the fine details of what is actually happening, we just simply need to have this abbreviation for that quantity here. It justifies the movement of this decimal point. Anyhow, very small, negative exponent. Okay. All right. Now, going back the other way, here is the second part of the file that is a PDF that looks like this. When you're converting from scientific notation to a decimal number, or what we call standard form, a regular number. Okay. Let's see. All right, now let me give you some ground rules in terms of the sign. When you start with a positive exponent, right, and you're trying to convert, this is for converting from scientific notation more or less to a regular number, i.e. a decimal or standard. Do associate the conversion for this sake with a direction. All right, you're going to move a decimal point towards the right, which is that way. Okay. If, on the other hand, you have a negative exponent, and you're still doing this, you're converting from scientific notation to a regular number, you're going to move the decimal point left, which is that way. Okay? And you basically will make waves. All right, we'll do two examples here for the sake of comparison. This quantity, let's see, 1.5 times 10 to the 8th kilometers is the distance, the average distance, because it changes, from the sun to the earth. .5 times 10 to the 8th kilometers, km. Sorry, it's a little sloppy. All right, what I do is two things. Number one, decide what the sign is here. If it's not written, what do you assume it is? Well, you assume it is positive if it's not written, all right? And then rewrite the number here just by itself and move that many spaces, all right, towards the right. So make 8 little waves. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to exaggerate the decimal point here, just not to confuse it with that. All right. Then you fill in the gaps, the waves here, with zeros. And at least if you're conforming to the stylistics, the peculiar way of writing here, you put a comma every 3, like that. All right, and then maybe clean it up a little bit to make it more legible. I'll spell it out. Kilometers. Which, if I spell it the fancy way, would be like that. R-E as opposed to E-R. Okay. It really, in the United States, we're a little defiant. We spell things backwards here, so this would be E-R. Right? Sorry. Anyhow, what is this quantity? It is 150 million. All right. The average distance from the Earth to the Sun is 150 million kilometers. All right. Just moving 8 decimal spaces. All right. Produces the regular ordinary number. And I'll pluralize that too, because I'm going to get yelled at by English people. Okay. Literary arts people, if you will. Language arts. Okay. Now, let's say we had an example like this to start with. 2.0 times 10 to the negative 5th millimeters. Okay. This is the diameter of the rhinovirus, which, if you think of a virus, is quite small, right? Normally they measure it, I would say, on the scale of nanometers rather than millimeters, which is another 1,000 down at least. Now, micro first, so it's 100, almost 1,000,000 times smaller than this, I think. Milli, then micro, then nano, I believe. 3, 3, and 3. 3 and 3. Okay, anyhow, 2.0 times 10 to the negative 5th millimeters is the rhinovirus, which I think is kind of funny because that's the common cold, all right? That's what causes the common cold. When you have, a stuffy nose or whatever. Biology people or have a sense of humor, like rhinos are famous for what? Having kind of a big nose. That's why I'm not in biology, all right? My sense of humor stinks. All right, anyhow. I'm happy with these. Again, associate a negative exponent with left. All right, so you're going to just simply duplicate, this decimal, 2.0. Maybe I'll make myself a little bit more room here. A little more room, 2.0. And move your decimal that many spaces. That many. Okay, so if the decimal's here, make 5 waves. 1, 2, 3, 4, 5. And then I'm just going to exaggerate that. Right? And then in the voids they created here, the waves, put zeros. So you would have, see if this is faint, 0, 0, 0, 0. Okay. Officially, this would be the number, just to write it a little bit more cleanly. 0.000, a little gap, because I'm trying to be a good American here. A little gap rather than a comma. That's how we do it here. I'm not saying it's better, it's just what we do. And if you want, you could put a 0 up in the front here. I'll make this little phantom 0, because it's supposedly to make this a little bit more obvious where the decimal point is. I don't know, that's debatable. Anyhow, what number is this if you were going to call it out? And it is millimeters. Still, tenths, hundredths, thousands, 10,000s, 100,000s. This would technically be millions if you read it all the way there. 20 millions. or you could say 200 thousandths, right, of a millimeter. Right, quite puny. All right. Anyhow, to simply say 0.00002 is fine. This extra zero on the end here is, depending upon if you have to include it for the sake of significant digits, fine to leave there, all right, or fine to exclude, for the same reason that it may not be necessary to put this here, all right. There may be some other rules in conflict with this. The decimal and the location of this 2 is what is most important. Okay, anything else is just gravy. Now the last thing is, well, we'll do some operations. Okay, if you have operations of multiplication, or division involving scientific notation. All right. The trick to this is to regroup. You don't have to do this, of course, but if you were doing it by hand, it would make your life a lot easier. All right. Regroup. When you've seen scientific notation, you know that it involves multiplication. So let's say hypothetically that you're multiplying one number in scientific notation times a second number in scientific notation. The only operation really going on is multiplication. And multiplication is commutative, which means that the order in which you write stuff doesn't matter. You could put things in any arrangement you like if it's a convenience for you. And that's really what regrouping would be. All right? You're going to group the decimals with the decimals. And you're going to group the powers of 10 with the powers of 10. Legally speaking, you could totally get away with that. Regroup. Similar situation for division. Let me give you an example. If you had this, -2 times 10 to the third, this is in scientific notation, just doesn't have a decimal point, it's not always necessary. And then in the second parentheses adjacent, you have 4 to the 10 squared. This is also technically scientific notation, it just lacks a decimal point. If it makes more sense to you, if it is a convenience, regroup. That is, put -2 together with 4, and 10 to the third together with 10 squared. Now you notice something. When I wrote the traditional Arabic numerals here, I used the multiplication X, which is optional. And in the case of the powers of 10, I put a multiplication dot. Does it matter? No, it doesn't. It's just that to me, this conforms a little bit more closely with the dot to the product rule, which has been established that if you have like bases, you're going to add these exponents, which means, and that is the whole point of this regrouping, this is going to be really 10 to the 5th. Right. Again, I more stylistically put this in the traditional sense as an X because everybody knows what 2 times 4 is, right? They won't be intimidated by that, even if it is a negative, right? Now we're following our rules of sign. A positive times a negative is 1 of each, so you get a negative. And 2 times 4 is 8, right? This is the product written in scientific notation. If you have, maybe I'll do this on, I'll try to squeeze it in here. I may regret this, but if you have a division problem, and it would probably be drawn like so. drawn as 3 times 10 to the third, sitting on top of 4 times 10 to the fifth. You can do the same thing. You could regroup. All right. So if you want, think of this as being 3 over 4 next to 10 to the third over 10 to the fifth. All right. This by itself, the powers of 10 portion of it, you can apply the quotient rule, which says that if you have the same bases, and for scientific notation, the bases are always going to be 10. All right, you're going to subtract these, right? Just be careful. If the 3 is on top, you're going to get a negative. So this is 10 to the negative 2. Save that. It just means that the quantity is very small, all right? It's not negative itself, the quantity, but that represents the power of 10 being a negative exponent just means that it's puny. As for this, 3 divided by 4, there's 2 ways I would approach this. I would start with trying to simply talk myself through it. If you read it instead of 3 over 4 in the more sort of colloquial context, 3/4, all right? Think of 3/4 in the literal context of money, all right? How many cents is that? This is 75 cents, which would look like that as a decimal, right? All right. Failing that, all right, you divide the top by the bottom with the decimal point and maybe throw in some zeros if it's necessary, all right, and then go through the process, right? In that event, the 3 would be here, and the decimal, and then you have some zeros, and the 4 would be here. 4 does not fit into 3, it's too small, but 4 goes into 30 roughly 7 times, which is the difference of 30 and 28, and that's a difference of 2, and then 4 goes into 20 exactly 5 times. Anyhow, look at what you get as a leftover here. You end up with this. The dud. I'm gonna throw that out. Keep picking up the dud. 0.75 times 10 to the negative second. Is this scientific notation? It looks very much like it, admittedly, but do remember, it is not technically scientific notation until you make the adjustment. We would have to scoot this over so that there is a non-zero in the front. Which means that you really should have this, 7.5 times 10 to, we're going to change the power of 10, the exponent specifically, all right, in order to compensate for moving 1 extra space, all right. This is a little bit tricky, and there's 2 ways to do it. You can convert it to a regular number first, all right, and then compare the end results. Or you could maybe attempt to memorize some rule. If you go farther technically, farther to the right, which is moving the decimal this way, moving from here to here is going further to the right. All right, that means that it is more negative. In this, starting with a decimal number that is in quasi-scientific notation. All right, that means you're going, and if it's only 1 space, more negative is amping up this 2 to negative 3. All right, if you feel a little uncomfortable with that, and I wouldn't blame you, all right, memorizing this because it has a lot of context behind it, you would have to take into consideration. You could always convert this to a standard form, a regular decimal number first, and then see if your end result matches as it should. Here's what I mean. If I took this from what it is, scientific notation, and put this in a regular number form, standard form, then it would be 1, 2, 3. It would be this decimal, 0.0075. What I have here should be the exact same quantity. If I took this decimal in front of the 7 in this case and moved it 2 spaces, 1, 2, all right, it would be the same exact quantity. So the alteration, the correction here to make this truly scientific notation is correct. All right, how come? Because what it really was to start with, 0.75 times 10 to the negative second, is what it ends with. These should be the same. And they are, if it's done correctly, 0.0075. Okay. Now here's the last thing, this discussion about your calculator. No one's going to get mad at you, of course. The calculator that you were expected to get from the beginning of the semester is this type, right? The TI 30XX, 30X Roman numeral 2S, which is a peculiar label. But just for the sake of consistency, all right, I can tell you what buttons to use on this. S, all right, calculator. If you have some other kind of scientific calculator, as long as it's a scientific calculator, which means it does scientific notation, not a graphing calculator, it's a calculator most likely that is in the 10 to $20 category. A graphing calculator, which has a much larger screen, is of the order of $100 or more. You don't need that for this class. All right. Anyhow, the advantage to having a calculator like this is exactly for what we've been talking about, scientific notation. You can get your calculator to do a lot of this for you. The underlying principles are important for you to know, all right? But to validate, verify, and give you a little bit of confidence, all right, check with your calculator as an afterthought, all right? Here are some buttons that are good to know on this type of calculator specifically. All right, first of all, if you wanted to type any power of 10, right, you would potentially need to use this button, which is referred to as caret, all right? If you had something like you wanted to type 10 cubed, all right, you would type the numbers 10 and then this button, caret, and then the number 3. And what you should see on your screen is something that looks like this, right? If you wanted to attach a negative either to the exponent or in front of the number, the actual base number, right? There is this button. Looks like an unhappy face. This is negative. All right. Not to be confused with this regular subtraction button. They're not technically the same thing. Now, in my view, using this and using this shouldn't be any different, right? However, the software engineers who designed the calculator may have disagreed with me, and they made a button specifically for negative. So if you want to attach a negative to a number, that's its coefficient, or the base number here, use this button rather than the regular minus button. Try to avoid using that unless you know you're subtracting. Then there's also these. You have buttons that are parentheses oriented like this and this. Parentheses. All right. I believe that is correct pronunciation. All right. This is for the purpose of, all right, to isolate, one number in scientific notation from another. Here's what I mean. If you were going to go directly to your calculator to do a problem like this rather than by hand. 3.7 times 10 to the 6th times 2.1 times 10 to the negative 2nd. I would, all right, just for the sake of syntax, which is, you know, conforming to the style in which the what's the word? The order in which you enter symbols into your calculator, all right, to avoid any error, all right, I would employ these parentheses, all right. So if you were typing something like this, you would type this open-ended parentheses here, then 3.7, the multiplication x, and then 10, and then the caret symbol, and then the number 6, and then close the parentheses. Right. You know how to enter 3.7, 10, and 6 naturally. Right. And then as an afterthought, do the next one. Hit multiplication, all right, then use this parentheses again, type 2.1, multiplication x, 10, the caret symbol, then the button that is designating this a negative, and then 2, I'm going to have to write that, and then close the parentheses, and then hit equals, you know, as an afterthought. And it will spit out the answer. Now, it'll probably spit out the answer in standard form, right? If you want the calculator to instead spit out the answer in scientific notation, you're going to have to change the mode of the calculator. If you hit the blue second button, and then this button, which is red DEG, or DRG, sorry, all right? You'll see a menu where you see flow, psi, and I think another thing called grad, perhaps. You will basically move the cursor over to psi, all right? And from this point forward, all right, the calculator will be in scientific notation mode. Which means all of the answers. The answer from having done this problem will be automatically in scientific notation. Yeah, I'll do it really quick to prove it. Okay. Here's your calculator. All right, I'm going to change the mode, second, and then DRG. And then you see these menus. It's a little bit faint because of the light. Flow, psi, and ENG. It's already, the cursor is already on psi because it's in scientific mode. So I'm going to hit enter. And we're fine. And now I'm going to proceed to type this stuff as you see it. I like to isolate the quantities that are written in scientific notation. Incidentally, here's the caret button here. See, it makes this little upward pointing arrow on the screen. I like to do this because I'm used to having my calculator give me errors if I put things in a bad syntax or a poor syntax. So it's just being extra careful. If you notice, I'll show you this here if it's a little bit faint. I neglected to type the multiplication x because I want to test the theory if I could get away with not pressing multiplication x for the operation that is really understood as being in between here. It should work, but sometimes it's better to be careful. 2.1 times 10, caret, negative. Here's that negative button on the very bottom. 2, close parentheses. All right, and there you have it. All right, I don't know if you could see this. 7.7 times 10 to the negative 4, to the positive 4. Let's see if I could do this the old-fashioned way without the calculator. It'd be shameful if I couldn't, right? I'm going to regroup. This is what the calculator is predicting. If this is 7.77 times 10 to the fourth. All right. Let's see. If you were to regroup, right, and you should be able to, then you put the decimal numbers together, and then you put the powers of 10 together, 10 to the sixth, 10 to the negative 2. And the benefit of regrouping is that you could apply the product rule. When you have the same bases, you're going to add these. Notice what you have. You have this situation where you have to basically add a negative quantity, right? It's the same situation basically as if you wrote it like this. Instead of 6 plus the quantity that is negative 2, just simply 6 minus 2. This is above a 10. All right. So even though the rule says add them, because of the signs that are involved, right, you end up spitefully subtracting anyway, which is why this is 10 to the fourth. All right. As for the decimals, I'm going to do this the brute force way. 7, 3. That's 1 times 7, 1 times 3, placeholder. 2 times that is 4. Carry this as 6 is 7. And you have 7, 7, and 7. And there are 2 decimal numbers. That is 1 decimal place and a 2nd decimal place that you must adjust this. So, as expected, it's 7.77 times 10 to the fourth. It's legit. Okay. Okay. Let me get out of that. Close this. Okay. Just some reminders. For homework, do section 5.6 now in my lab. Right. This is through Canvas. I haven't talked to many of you, well, several of you. I know that there were some issues. All right, firstly with logging into Canvas, especially last night. That's not your fault. That their server is broken for whatever reason. I didn't record the grade that I had wanted to do today, actually last night, midnight, or 11:59 p.m. For that reason. All right. Until this gets fixed, all right. I just want you to please stay current with the homework. All right. So since we covered section 5.6, you really should be doing section 5.6 at this point in the semester, all right? If you're a little bit behind, just catch up, all right? What we'll be doing on Wednesday is section 5.4, right? It's a lot of whack. I didn't design that. It's the order in which somebody else decided it. Anyhow, just try to catch up and try to do this today, all right? Or at least during the week, all right? I'm gonna have to eventually give you midterm grades. They're not a midterm test, all right? They're just like the early warnings that you had early in the semester. And if you were here for fall, all right, you may remember that there's an early warning, a midterm, and then there's the actual final grade. It's only the final grade that counts for anything. These other 2 grades, early warnings and midterm grades, are more or less as a courtesy. It's kind of to light a fire under a person to get them to do stuff. Anyhow, we're in, kind of a weird situation here. All right, so I don't want you to worry, all right? If you see a midterm grade, it's only because they obligated me to do it, all right? And don't take it too seriously. It's either going to be an S, as in satisfactory, a D, or an F, which are intuitive, all right? Nobody's getting an F, all right? If you see a D, it just means catch up, all right? Some of you didn't update the software license yet for whatever reason. Perhaps you're out of work, all right? And I understand. Just for the sake of grades, in the long run, we're going to basically be off the campus for the rest of the semester. You just want the experience, so you want to have the material, you want to have access to the material. So if you can, please make sure that you update your software license. If you somehow created an account, not through Canvas, all right, but through the Pearson website, you got to call them, all right? And you have to merge these two accounts. So I have for the longest time in the semester been chasing after 3 or 4 people, all right? You got to call the Pearson people when they're actually there, all right, please, all right, and get them to merge the accounts, because if I can't see your grades, I can't give you a grade, okay? Not to be a nuisance, just I need to have access to the material, okay? And you do too, more primarily, more importantly, for the sake of experience, all right? I'll see you on Wednesday. Be careful out there.